Games. We generally think of them as, the opposite of work, right?
Sure. Escapism.
It's what you do to procrastinate. You play some Mario Kart, you set up the chessboard to feel, I don't know, sophisticated.
Or crush your siblings in Monopoly.
Exactly, to assert dominance. It's an escape. But if you actually look at the history of computer science, games, they aren't a distraction at all. They're the laboratory.
That is a great way to frame it. They are the ultimate testing ground.
They're the dojo where artificial intelligence learn to fight. And today, we're not just going to recount the famous matches where the robots won. We're going to look under the hood.
Right.
We're going to break down the actual algorithms, the logic that allows a pile of silicon to, predict the future and dismantle the greatest human minds on the planet.
It is a fascinating topic. And to guide us, we're doing a deep dive into a really comprehensive lecture module. It's from California State University, Channel Islands, taught by Dr. Reza Abdali. And it actually adapts some core AI concepts from UC Berkeley, so we're really getting into the gold standard of computer science theory here.
So our mission today is to understand the mechanics of that whole man versus machine narrative. We all know the headlines, Deep Blue beating Kasparov, AlphaGo shocking the world, but we rarely talk about how.
Mm-hmm.
How does a machine that doesn't know what a king or a pawn is, and certainly doesn't feel pressure, how does it manage to outsmart a grandmaster?
And the answer is often, surprising. It's less about intelligence and the way we experience it, like some flash of inspiration or a gut feeling, and more about just raw mathematical elegance. Slides call it behavior from computation.
Behavior from computation. I like that. It implies that if you just do the math fast enough, it looks like thinking.
Precisely. And in a lot of cases, that is all you need to win.
So let's start with what the source material calls the Hall of Fame. It's basically a timeline of AI progress, and it tracks perfectly with the complexity of the games we challenged computers to play.
It's like a hero's journey for the computer, yeah. Starting with the simple stuff.
And the entry point was?
The entry-level drug for AI was checkers.
Checkers. The kind you play on a porch. Pretty simple rules. Why was this the starting line?
Well, computationally, it's just manageable. The board is 8 by 8, but you're only using half the squares. The first computer player was developed way back in 1950.
Wow, that early.
But the real story, the one that really signaled the end of human dominance, that happened much later, in 1994.
This has to be the Chinook story, right?
Yes, Chinook. It was a program from the University of Alberta. And in 1994, it became the first computer to win a world championship in a game of skill. It ended the 40-year reign of a human champion named Marion Tinsley.
40 years. That's hard to even wrap your head around. Imagine being the absolute best in the world at something since the Eisenhower administration.
You're unbeatable.
And then suddenly you get taken down by a script running on 90s hardware. That has to be a psychological blow.
It was a huge moment. But the timeline gets even darker for the humans. By 2007, checkers wasn't just dominated by computers, it was solved.
Okay, solved is a heavy word. In the context of these slides, does that mean what I think it means?
It means the game is dead, mathematically speaking.
Yeah.
A solved game is one where the computer can look at the board from the very first move.
Before anyone's touched a piece.
Before a piece is even moved.
Yeah.
And it knows the perfect outcome. They prove that if both sides play perfectly, checkers will always, 100% of the time, end in a draw.
So it's like tic-tac-toe.
Exactly.
Once you know the trick, you can never lose.
Exactly. Just, much more complex. But that complexity is finite. Which brings us to the next level up, the heavyweight division.
Chess.
The fruit fly of AI research. That's the classic nickname for it.
And this is where we get into the brute force era.
Right. And the main character here, of course, is Deep Blue.
1997. Deep Blue versus Garry Kasparov. I remember the news coverage for this. It wasn't just a game. They framed it like a battle for the survival of the human species.
It definitely felt that way. Kasparov was the world champion, arguably the greatest ever, and Deep Blue beat him in a 6-game match. But what matters for us today is the scale of the computing.
Okay.
The source notes that Deep Blue wasn't just thinking. It was examining 200 million positions per second.
200 million per second.
It was using a custom-built chip just to generate moves. And it wasn't just looking at the next turn. The slides mention it looked up to 40 ply ahead in some variations.
Okay, let's unpack ply. I'm assuming we're not talking about toilet paper sickness here.
No, not quite. In game theory, a ply is one turn taken by one player. So if I move a piece, that's 1 ply. Then you move, that's 2 ply.
So 40-ply means it's calculating 20 moves for white and 20 moves for black, deep into the future.
Deep into the future, it's staggering. Humans, even grandmasters, they can't hold that much data in working memory. We rely on intuition, on pattern recognition.
This looks like a strong castle structure, that sort of thing.
Exactly. Deep Blue just drowned Kasparov in calculation. It was a tsunami of data. But even Deep Blue had its limits. Which brings us to the final boss.
Go.
The game that stood as a wall against AI for decades longer than chess. Go.
The ancient Chinese game, Black and White Stones. It looks visually simpler than chess. It's just stones on a grid. But the math is a nightmare.
It's an exponential nightmare. To understand why, you have to look at something called the branching factor.
Okay.
In chess, on any given turn, you have roughly 35 legal moves to choose from. We call that B.
So every turn, the tree of possibilities splits 35 ways.
Right. In Go, the branching factor is greater than 300.
Wow. So for your first move, you have 300 options. For the opponent's response, another 300.
Exactly. I mean, if you tried to use Deep Blue's brute force method on Go trying to look 40-play deep, the universe would literally undergo heat death before you finished calculating the first move.
So you can't just muscle your way through it with faster chips.
No. And that's why 2016 was such a shock. AlphaGo didn't just calculate faster, it learned. The slides highlight that it used something called Monte Carlo tree search combined with deep learning evaluation functions.
So it basically developed an intuition. It didn't look at every single path. It learned which paths were worth looking at and just ignored the rest.
Precisely. But to understand how any of this works, whether it's the brute force of Deep Blue or the intuition of AlphaGo, we have to go back to basics. We have to look at how a computer actually sees a game.
Right, because it's not seeing a wooden board or feeling the tension in the room.
No, it sees a data structure.
The source material has a section on formalizing games. This feels a bit abstract, but it's really clarifying. It lists 4 main components that define a game for a machine.
Right. If you want to code an AI, you need to define these 4 things explicitly. First, you have states, which is the letter S. This is just a snapshot of the world.
Where are the pieces? Whose turn is it?
Exactly.
Yeah.
The board arrangement at any given second. Second, players, or P. Who has control?
Okay.
Third, actions. A. What are the legal moves available from the current state?
So knight to f3 is an action. Pawn to e4 is another action.
Correct. And fourth, and this is the engine of the whole thing, the transition function. It's usually written as S times A leads to S.
Which translates to what exactly?
Translates to, if I am in state X and I take action Y, what is the resulting state Z? It connects all the dots. It's the physics of the game world. It tells the computer how the world changes.
Okay, so we have the board, state, the movers, players, the moves, actions, and the rules of movement, transition.
Once you have that framework, the slides say you can categorize games into different types. And the 2 biggest distinctions are deterministic versus stochastic.
Deterministic means predictable?
It means no randomness. Chess is deterministic. If you move a pawn, it goes there. There's no die roll that says, oops, your pawn tripped and died.
Right.
The outcome of an action is 100% certain.
As opposed to something like backgammon or poker.
Exactly. Those are stochastic. They involve chance rolling dice, shuffling decks. The AI for those is totally different because you have to calculate probabilities, not just pure strategy.
And the other big category is information.
Right. Perfect versus imperfect information. Chess, Go, checkers, Pac-Man, those are perfect information games. You can see everything.
The enemy can't hide a rook in their pocket.
Exactly. Compare that to a card game where you don't know the opponent's hand. That's imperfect information. So the classic AI victories, they were in these deterministic, perfect information environments.
Mostly.
But there's one more term from the source that defines the attitude of the AI. Zero-sum.
I hear this term in business meetings all the time, usually incorrectly. It's a zero-sum game. What does it actually mean in the strict game theory sense?
It means diametrically opposed goals. It means there is a fixed amount of utility or value in the game. If I win, I get +1. That means you must get -1.
The sum is 0.
The sum of our scores is 0. So cooperation isn't just impossible, it's irrational. Helping you directly hurts me. And this is crucial because it lets the computer make a very specific assumption about its opponent.
Which is?
It assumes the opponent is a rational agent who is trying to destroy it.
And that assumption is the foundation of the whole strategy, which leads us to the visuals in the source, the game tree.
Game tree, exactly. And visualizing this is absolutely key. Imagine the current state of the board is the trunk of a tree.
Okay.
From that trunk, branches shoot out for every possible legal move you can make.
So for simple example, if I'm playing Pac-Man and I can go north, south, east, or west, that's 4 branches right there.
Right. Now follow the north branch.
Yeah.
That leads to a new state.
Yeah.
From that state, the ghosts move.
Right.
That creates new branches. Then you move again. More branches.
It's a multiverse. Every single branch is a different timeline of the game.
That's it. And the tree grows exponentially deeper and wider with every turn. The computer's job is to navigate this massive, sprawling tree to find the one timeline that leads to a win.
And the algorithm for that is the star of this lecture.
Minimax.
Minimax. It sounds like a Bond villain, but it's actually just a description of the logic, right?
It is. It describes 2 agents, Mac and MIN.
Okay, so let's role play this. I am MacX.
You are Max. You want to maximize your score, your utility. You want the plus 100, the win.
And MIN is my opponent.
Right. And remember, it's a zero-sum game, so MIN wants to minimize your score. MIN wants you to get minus 100.
So it's a recursive dance. I'm looking for high numbers. MIN is looking for low numbers.
Yes, but here's the trick, and this is what makes it an algorithm. It works backward.
Backward.
It looks all the way down the tree to the terminal states, the end of the game where someone has actually won or lost. It assigns values. Checkmate for white is plus 100. Checkmate for black is minus 100. Then it bubbles those values back up the tree to right now.
That feels abstract. Let's walk through an example. Say I'm X, and I have to choose between move A and move B.
Okay, let's play it out. You look at move A, you see that if you make move A, it becomes MIN's turn. And from there, MIN has 2 choices. One leads to a huge win for you, plus 50. The other leads to a mild gain, plus 5.
Well, obviously I want the plus 50. That sounds great.
Of course you do. But MIN is playing, and MIN is rational. Is MIN going to just give you the plus 50?
No, MIN hates me. MIN is going to choose the path that gives me plus 5 because that is the lowest score available for me.
Exactly. So in the eyes of the Minimax algorithm, the value of move A is effectively plus 5. You have to assume the worst. The plus 50 is a mirage because a smart opponent won't let you have it.
Okay, I see. Now what about move B?
If you take move B, MIN has a choice between giving you a plus 10 or giving you a minus 100.
Oof. MIN is definitely slamming that minus 100 button.
Right. So the value of move B is minus 100. Now you're back at the start. Your real choices are move A, which leads to plus 5, or move B, which leads to minus 100.
I take move A.
You take move A. It's not the dream scenario of plus 50, but it avoids total catastrophe. That is Minimax. You maximize the minimum guaranteed gain.
It's a very pessimistic algorithm. It assumes the opponent is perfect and absolutely ruthless.
Which is the safest assumption in a world championship match. The slides actually show the pseudocode for this function, literally called max value and min value. They just ping pong back and forth until they find the truth.
But wait a second. We talked about Go and the universe ending problem. If Minimax requires going all the way to the bottom of the tree to find these terminal states, doesn't it just crash into that wall of complexity we talked about?
It absolutely does. The source material is very honest about this. It asks, how efficient is Minimax? And the answer is
not very.
Terrible.
At least they're honest.
It acts like a depth-first search. And the math here is brutal. The time complexity is written as O of B to the power of M.
Okay, let's translate that big O notation for everyone.
Sure. B is the branching factor, how many moves you can make, and M's the depth, how many turns the game lasts. So the time it takes is B multiplied by itself M times.
Exponential growth. So for chess, B is 35, M is maybe 100. So that's 35 to the power of 100.
Which is a number with more zeros than there are atoms in the observable universe.
Yeah.
The slides explicitly say that solving chess exactly is completely infeasible.
So how did Deep Blue do it? It obviously didn't solve the whole game.
No. Computer scientists had to get clever. They realized 2 things. 1, you don't always have to go to the very end. But 2, and this is more important, do we really need to look at every branch?
And this is a section on pruning.
Like gardening, you cut off the dead branches so you don't waste energy on them. The specific technique here is called alpha-beta pruning.
The name sounds technical, but the logic is actually really intuitive, right? It's about not wasting time on scenarios that are never going to happen.
Exactly. Let's go back to our example. Remember, move A gave you a guaranteed plus 5.
Right. I have plus 5 in the bank. I know for a fact I can get at least that much.
Now, you start analyzing move B.
Mm-hmm.
You look at the very first response MIN could make, and you see it results in a minus 100 for you.
Whoa.
Now, here's the question.
Yeah.
Do you need to keep looking at the other responses to move B? What if there's a plus 1,000 hidden somewhere else in that move B branch?
I don't care. It doesn't matter. Because I know one of the options is minus 100. MIN will see that minus 100 and will absolutely force me to take it.
Yeah, and since that's worse.
Since minus 100 is way worse than the plus 5 I already have secured in move A, I can just stop thinking about move B entirely.
Precisely. Max will avoid it, so we can stop considering the other children. You prune the entire branch. You don't even look at the other possibilities because you know a rational opponent has already ruined that path for you.
That's brilliant. It's efficiency born out of, I don't know, fear. You see one bad thing and you just say, nope, not going down that road, and you save all that computing power.
And the efficiency game is massive. With perfect pruning, you can effectively double the depth you can search in the same amount of time. That's the difference between a decent player and a grandmaster. That is how Deep Blue got to 40 ply.
So we've gone from the definition of a game, the physics, to the game tree, to the Minimax strategy, and finally to pruning to make it actually computable.
It's a complete system for decision-making.
And while the lecture focuses on games, you have to realize these are general-purpose algorithms. This is about decision-making under pressure. It's about optimizing outcomes when there is an adversary.
It applies to economics, to wargaming, to negotiation.
Anywhere you have rational agents with opposing goals.
The math doesn't care if it's chess pieces or market shares.
It really changes how you look at a chessboard. It's not just wooden pieces, it's a visual representation of this massive invisible tree search that's happening in real time.
And the history we covered, from 1950 to 2016, it just shows how quickly we mastered that search. We went from teaching a computer what a square is to building entities that can out-strategize the entire human race in our most complex creations.
It is humbling, and it leaves me with a bit of a provocative thought to wrap up on. We talked about checkers being solved. The mystery is gone.
Right, it's just execution now.
As computing power scales and these search algorithms get more and more efficient, are we moving toward a world where strategy ceases to exist? Because strategy implies, guessing or risk or deception. But if the computer can see the end from the beginning, is it really a game anymore?
Or is it just a puzzle that's already been put together? That is a deep question. If the optimal path is known, then any deviation from it is just an error.
Right. Creativity might just be a nice word for suboptimal play.
Ouch. That's a tough one for the artists out there. But mathematically, you might be right.
Something to mull over the next time you lose a game of Connect Four to your nephew.
Maybe you're just being creative. I'll tell myself that.
A huge thank you to Dr. Abdali and the resources from CSU Channel Islands for providing the roadmap for this discussion. And thank you to you, the listener, for climbing down the game tree with us.
It's been a pleasure. Keep optimizing your utility.
We'll see you on the next deep dive.